Ionization, the word ionization means to make an ion. And in this case, how do you make an ion? By removing an electron. So when you have a nucleus, and let's say you have the first shell and the second shell, and you have, let's say you have the electrons here, the first shell, and let's say you have an electron in the third shell, and the second shell. In order for you to move this whole thing outside of the atom to make an ion, you have to use lots of energy, comparably. Okay, to make this one, to fling this one out, you have to use a large amount of energy, comparably to the transitions, n from n smaller to n larger, so on and so forth. And that's what energy is that? That's called ionization energy, IE. We're not going to talk about second and third ionization energy. We can talk about it later, but for now, we're just going to focus on first ionization energy. I'm going to say that, and I wanted to show you this about the atomic radii, how the size decreases from left to right, as you can see. There are, of course, some exceptions, but overall, that is to be followed. So let's look at ionization energy. What you need to write about the ionization energy is that it is the complete opposite to atomic radius. So what that means is know one, and then the other one will be complete opposite. You don't have to know both. And that's a good skill for tests, not only in this class, but any entrance exams where you have plenty of information, but you have antithetical relationships. So you only know one and you say the other one is the opposite, rather than just saying, okay, this one is the opposite, or this one is this, and that one is this, and that one is that. Too much on your brain. So just know one and say the other one is the opposite. So the ionization energy increases from left to right. There's some exception. And the ionization energy decreases from top to bottom. So it goes like this. IE stands for ionization energy. Actually now increases. It's opposite. But it decreases from top to bottom. And the reason why is because the effective nuclear charge gets bigger. ZEF is larger, while ZEFF is smaller. Sorry about that. Let's see. That would be the explanation, the conceptual explanation. Okay, very well. So let's go back to this. How do I apply this here? Well, you keep that line drawn, and now all you have to do is say ionization energy going from this corner right here, lower left-hand corner, all the way to the upper right-hand corner. IE increases. IE increases. So let's apply it to the one we just did. And instead of now saying atomic radius, we're going to say ionization energy. So what would happen here? The complete opposite. So we're going to circle them here. We have P, Na, we have F, we have K, we have O, and we have CS. Notice that F now will be your highest. So what's my smallest? It would be the CS because it's the lowest. It increases as you go this way. So that would be CS is smaller than K, then NA, then PA, then P, I'm sorry, and then O, and F is the highest. And metallic character is nothing that I'm going to do. It's the same as atomic size. Basically, what behaves more like a metal, more like a non-metal. Well, you follow the atomic size. As you go from left to right, the metallic character decreases, and you go down, the metallic character increases. Where is this particularly important? Over here, especially on this right here. So metallic character decreases. Where is it more particularly important? Down here. Down here. For example, nitrogen is a nonmetal. As you go down, the metallic character increases. P becomes next. It's still not metallic. Arsenic is now exhibiting more metallic. Then antimony. Then bismuth is a full metal. So as you can see here, as you go down, bismuth would be the most metallic in that group. In group 15, let's say.